Hi, I'm Chris. I've been working on the propulsion, and as we showed last week, this is how we split the work. I've been working on the underwater systems and the batteries. At the end of the first week, we chose a pump jet based on those advantages there. And then I've looked at some existing pump jets. Unfortunately, most of them have a much higher power requirement than what we actually need, and they also for service high-speed boats. So they take in water from the bottom, and that's not really ideal for a completely submerged pump jet. So what we ideally want is something like that. Pump jets in the submarines are still quite a new idea, so there's not a lot to choose from. So I'm going for a new, completely new custom design. And the idea is to basically have a conventional pump there that increases the pressure, and then a converging nozzle that gives you the delta V, and the boat will be housed in here. So I'm going to quickly talk through how I designed it. Firstly, to pick the type of pump, there's two main categories: a displacement pump and a rotodynamic pump. Displacement pump is basically just pushing the fluid back, similar to a paddle wheel. A rotodynamic pump is much more common in pump jets. They're usually smaller sized. I'm not going to go through all the different types, but from the equation you can see for the best propulsive efficiency, you want to decrease delta V. To get the same thrust, you need to increase Q. So from this graph here, on the left we have the head rise, which is essentially a pressure rise. So that's directly related to delta V. Bottom we have the volume flow rate, so we want a high volume flow rate, low head, and that points us to an axial flow pump. So using some industrial parameters, thrust is equal to drag at 5 knots, which I got from Hydro, and Q at the moment I just picked 1. It's a typical value for a large axial flow pump, but that can change later on in the optimization. So that gives me the delta V. Using delta for pump design, mostly they're not actually for propulsion, so I have to convert that to a head rise, and that's through that formula. So just think of that as the increasing pressure, increasing energy. The inlet head, HSV, is basically similar to the atmospheric pressure. And then the suction specific speed is a dimensionless parameter they use. I picked 0.5 at the moment. That's typical for a pump under prolonged duration. And as you can see, that then gives us the rotational speed. My design is based on an empirical approach by Turton and Stepanov. The overall efficiency from what we've got at the moment is 0.77, is quite low, but again that can change later in the optimization. And then using that we get the power required of 62.5 kilowatts. That then gives us a total requirement of 100 kilowatt hour, slightly higher than the 80 kilowatt hour we got last week. And then we get the specific speed, basically very similar to the suction specific speed. And then using that value and some empirical data, we get a number of blades, axial velocity in the inner area. Similarly, we then get the hub to tip ratio and the diameters we want. We then also assumed a hydraulic efficiency. That's basically directly related to the CL over CD of the airfoil. At the moment it's assumed, but later, once we pick the airfoil, we'll iterate and find where it actually is. So using that, we get the actual head rise, which then determines delta U. And then using delta U, the axial velocity and the rotational speed, we get the fluid inlet and outlet angles. At the design point, we want the fluid inlet and blade inlet to be the same. Whilst the fluid inlet outlet angle, we have calculated using the deviation, which is done using the empirical formula there. For P over C, the position of maximum camber, we take 0.4. That's based on some research which shows that it's most common in fan and pump blades, and it's best against cavitation. I've also used knackered 4-digit airfoils at the moment, just because they have a well-defined equation, so I can easily go from the camber and the P over C to the actual airfoil shape. And also note that having defined B to 1, the camber and the airfoil shape, that then gives us a angle of attack. So based on that angle of attack, we then pick the airfoil with the best CL over CD. So this is what I've got at the moment, having done the analysis for the tip and the hub. It's quite all the parameters are quite connected quite complexly. So that was going through iteration. and those are the airfoil we use. It's not quite those, it's a slight modification. And note the large angle of attack for the hull. I'll talk more about that later. And then using these two equations, which are derived from just lift and drag acting on an airfoil, you get the hydraulic efficiency. And this equation gives you the chord that we need. So that essentially you have to find the blades we need. A similar thing was done for the stator, again quite high angle of attacks. Try to reduce that by decreasing the area at the stator, which increases our axial velocity, and also not actually completely removing the swirl velocity. That additional thrust there, 559 newtons, is the additional thrust we get by getting back some of that extra swirl energy. I then had a brief look at cavitation. At the moment it's just based on CP plots. There's more accurate, some empirical methods, but at the moment it's just an initial idea of what will happen. To make sure cavitation doesn't happen, the minimum pressure has to be above the vapor pressure, which is from that empirical equation, based depending only on the temperature. And so using the CP plots and the atmospheric, well not atmospheric, but the surrounding pressure, you get a minimum pressure of 89 kilopascals. So that's way higher than the vapor pressure. So for this current design, we should be safe. As I've said, there's some quite angle of attacks for some of the blades. So that could potentially stall the blades, so we're going to have to consider that in the optimization. And the variables we can change are the volume flow rate, the suction-specific speed, the airfoil, and the position of max camber. The restrictions are firstly, obviously, the weight, secondly, the inlet size. Bear in mind that in flight, we're going to have to cover up the inlet, so the bigger it is, the more complex that would be. Thirdly, the amount of space we have, but according to systems, that shouldn't be too big of a problem. And lastly, cavitation. So at the moment, we're safe, but if we increase the RPM, that might not be the case anymore. And then now I've had a brief look at the inlet geometry. I quickly drew this on the page. Sorry for just facing you on all over the world. If you have the inlet sticking out at the side, you have to protrude into the flow, like the diagram at the top right. And the hydro guys have strongly objected me putting anything at the bottom of the hole in the stock area. So if it's going to the side, we'll have to go to the side like that, and also upwards to the lighter area there. Alternatively, we could go all the way to the front, just as the straight line shows. So I then had to look at the losses in the different geometries. There's mainly two different types, one by friction, which they call a major loss, and one due to the bends in the pipe, which they call a minor loss. It doesn't necessarily mean major is larger than minor, it's just the name. The major loss was calculated through an empirical formula there, and the Moody diagram. And the minor losses is using typical loss coefficients, as you can see from that table there. You say roughness of, relative roughness of 0.101. That's based on typical pipe roughness and also our diameter. So this is the number we get. As you can see, clearly the straight ductors are by far the best. That's partly because the one that goes to the side, you have 2 times the, well, it has 2 dots going to either side for symmetry. So the straight duct is probably what we're going to go for. Next, having defined the inlet, next week I'll be working on the nozzle, which is essentially just decreasing area, so the pressure goes back to the surrounding pressure, and then we get the delta V. And then I'll be doing some inlet and engine optimization, choosing an electric motor, battery layout, so things like whether it's series, parallel, how far they'll be separated, and lastly the materials. I've had a brief look. Steel and titanium have the best cavitation erosion resistance, but obviously steel is heavy, so at the moment it seems like titanium is the most likely for the blades. And that's it for me.
I like it. Yeah. It's more my style. One thing I've missed, what are your inputs to start the calculation? So what is it that you want to achieve?
I want to, well, for the pump jet, I want to make a basically pump jet that can provide enough thrust to counter the drag
So you know how much thrust you need to go at a certain speed.
Yeah. Well,
Were you told by somebody?
yes, from Martin from Python.
Okay, so that calculation is done.
Yeah. Well, it might be an estimate computation, but we're going to have to optimize it later. So
I'm pretty sure the direct calculations are finished, but it was, I'm not sure because Martin is not here, but I believe they were an estimate.
Yeah. Okay. But it can be easily changed.
Okay.
Yeah.
Yeah, of course. So how much is the thrust you need?
6 kilonewtons.
Not a lot. 600 kilos. A horse.
Well, it's only going at 5 knots. So
5 knots.
You mentioned an efficiency of 77%,
Yeah.
all things included. I expect that's just for the pump without the
Yes.
losses of the intake, right?
No, that.
Or is that's just the pump, not
Yeah.
the entire propulsion?
That's just the pump. Yeah.
And you said that's going to go up. What do you expect the
Well,
maximum you'll be able to reach it?
well, from that plot there, it's around 0.9 millimeters. So that's.
Okay. And so what is it in your design right now that is actually stopping us from going 0.9? You're about 13% below.
Yeah. We could be trying to increase the mass flow rate. So it would just be based on this diagram, trying to reduce KS. So that'll be maybe reducing the rotational speed perhaps. But I mean, there isn't anything stopping me. It just takes some values at the moment.
So this is just random inputs, basically, or normal values.
Yeah.
Okay. Looking at your airfoils, you referred to using NACA 4 series
Yeah.
airfoils. At the tip, you have no camber whatsoever?
Yeah, it's not exactly those. It's slightly modified. It's like 0 point something. So,
Okay. But out of all this, what I find very surprising is the 20% thickness to chord ratio at the hub.
yeah.
Is there a reason for that?
I found that increasing the thickness increases the CO visibility, and it actually just kept going beyond 20, but because 20 was it's really quite thick, I've limited it at 20.
Okay. What kind of analysis was this? Was this viscous or inviscid?
It's viscous.
Okay.
And your power requirement is based on travelling at 5 knots or whatever in quiescent flow, presumably?
Yeah.
Okay. What about when you're manoeuvring?
I haven't considered that, but it depends how much we have to maneuver. If we can just go in a straight line.
Yeah, so I think it might be worth designing some redundancy into manoeuvring or even a tidal
Yeah.
flow, for example.
So
If there's a 4 knot tide, then you're stuck at 12 nautical miles out.
yeah, that's true.
6 knots. I hear
Yeah.
We've considered a factor of 1.5 when we got the 1
Okay.
kilowatt hour. That is just a guess.
For the cavitation work that you did, you chose a temperature of 300 knots from what I see.
Yeah.
Is it normal for 15-degree, 17-degree temperatures at 30 meters below surface?
I've looked at some plots with temperature variations, and initially for the first, up to at least 33 meters anyway, in the fleet, it doesn't change that much.
Okay. And so would you have to consider a best case or a worst case scenario over here? A very, very cold day or a very, very warm day should be considered here?
So a cold day give a higher pressure. I think.
So, just more of a comment on the presentation. I very much liked the systematic way that you've gone through it. It's very good. From the point of view of someone that doesn't know anything about pumps, you have quite a lot of terminology of head rise, inlet head, fluid inlet angles. You had a lot of things you were calculating. You think it would have maybe been a little bit clearer to sketch the diagram yourself, but leading the viewer through the process rather than just a sort of list of numbers and phrases.
Yeah.
Would help me.
Okay. I know it's hard to explain it in 10 minutes.
Similarly for equations, avoid just flashing an equation and moving to the next slide. It's probably the most annoying thing that anyone ever does,
Okay.
for me anyway. Otherwise it's good.
Yeah, I agree. This is very nice presentation. Just one other quick thing. So, from what I gather, you're going to take inlet from the very front of the plane
Yeah.
and draw it all the way to the back. Do you have an idea of the boundary layer growth that you're going to have in that gut? Because I think you may find that certainly the tips of your blades, but maybe significantly more than the tips of the blades, are going to be in the boundary layer effectively.
Yeah. I haven't looked specifically.
And so then we have a much slower velocity than we might expect going to the blade.
Might do something to maybe.
Because obviously a shorter gut you have less boundary layer growth, so that's the problem that it seems like with the instructors you have to have this long gut, so that's something that probably worth considering.
Okay.
Because your blade aerodynamic performance profiles, so you quoted some values of CL, yeah, and L over D. Yeah, go back. Yeah. What program did you use to get those?
This is from Java.
Okay. Do you believe them?
No.
Okay, good. So you very early on dismissed the idea of using off-the-shelf techniques, or sorry, off-the-shelf products, which you said were about 100 kilowatts or more.
Yeah.
And okay, so the mismatching in the power I can understand, but I don't know. You want 40 kilowatts, 42 and a half kilowatts. So then there are designs out there for 100, or
Obviously, the smallest is 100.
okay, but is that not sensible to consider? What do you think the cost implication is of everything you're proposing here? How long do you think it would take to put an engine like that from your head into practice?
I think
So,
in production. Years maybe. But I mean, the whole aircraft is brand new, so I guess we can subcontract those choices.
okay, but you've considered that. You think the advantage of using something off the shelf that's tried and tested for 20 years on speedboats is not as
I haven't thought that much about it, but
You're gonna
it's the existing one because partly because they're not optimized for what we need, and I actually can't get the thrust from them because I don't know the geometry, blade profiles, or anything what they horsepower.
okay. So all the effort you're going to will give you an engine that's better matched. But what's the advantage of it? Is it going to be 10 kilos lighter?
Hopefully, it uses less power, so less battery. Yeah.
Okay. So you're saying the other pumps can't operate at below their maximum power?
So they can, but maybe not optimal for what we need.
Okay.
I can't get the first one.
Okay. Your tip to hub ratio is quite large. So
Again, that can change as we adjust